Welcome to LFPL's At the Library series, an ongoing podcast featuring author talks, programs, and events at the Louisville Free Public Library. For more information about upcoming events, visit us online at www.lfpl.org/upcoming-events.htm.
Good evening. It really is a beautiful evening for this. We dialed it up. It's really, really perfect for this. As you who were here last week know, today we are going to do something special, but we're not doing it just yet. There's some recap to be had before we go outside, but we are all going to go outside, and I'll tell you how we do that once we get there. And the tree is on this side, but before all that, please give your attention to Dr. Rochner. She's going to kind of bring us back up to speed for those of you who may have missed the first class and get you ready for what we're going to do outside. So thank you.
All right. Hello, everybody, and welcome back to our second round of classes on tree rings. Thanks again to the library for having me. I see a lot of familiar faces, so good to see y'all coming back for round two. If there are new faces in the crowd, I thought I would just spend some time talking about sort of a little bit of a recap so that you're oriented to what we're going to go do outside. And also I had mentioned the opportunity to hear about the things we talked about in week one over and over again. But we're going to get into more specific applications as we go throughout the courses, including applications here in Kentucky, close to home, here in the city of Louisville in our state of Kentucky. So you can see what I'm doing with tree rings here at home. So just to sort of recap on, I think, what is dendrochronology. And first, I am Dr. Maegen Rochner. I forgot to introduce myself again, from the University of Louisville, and I'm a tree ring scientist. What I do is, I think I took a poll last time of how many of y'all have looked at tree rings before, and almost everybody had at some point. You were familiar with that you could use them to figure out how old a tree is. You can look at the ring list to think about how it has been affected by climate and other environmental change through time. So many of us have probably walked by a stump at some point and paid attention to its rings. Every time I see this, I definitely pay attention. I'm looking for rings everywhere. I said last time, at the end of the bar, in a table, in the floor. Everything made out of wood is usually catching my eye. I like to see how old the tree was that was used to make this product. What I do, now sometimes I might actually take a section off of a stump or off of an already downed tree. I don't kill any living trees to get at this information because I don't have to. What I do and what we're going to do outside is I take an increment core. This is just a tiny little core out of the tree across the cross-sectional view. So what you look at a stump when it's been cut clean off, I'm sort of coring through that same view. We call it the cross-sectional view. And I can see all of the rings in that core. They're pretty tiny, as you're going to see. They're like 4 to 5 millimeters. They fit in a paper straw. They're smaller than a pencil. So take a pretty tiny amount of living tissue from that tree, and usually it will fill that hole in pretty quickly with sap, with resin, because it sees it as an injury and it sends something to it to seal that off and keep anything out. We extract that core, we sand it down, we put it in these wooden core mounts. I brought the examples back again today in case folks want to look again. So the core itself is round, but we put it in these square mounts so it's easier to hold because I actually have to hold it upside down against a belt sander. And I don't want to be holding something that's 4 millimeters against a belt sander. And it also just sort of keeps things tidy, keeps it in place. We sand it, we end up with something like this. This is just a mock core again. And I've done it as a conifer with the light parts being the early wood or the early growth of the year, and the dark parts being the late wood or the later growth in the year. When you look at a conifer, you see these light and dark bands. One light and one dark together equals 1 year. It's different, as we'll see when we take a core from an oak, when you talk about hardwoods. And we'll talk about specifically oak as an example when we go outside. What I study as a tree ring scientist are relationships between the growth rates of the tree and other evidence of trauma that I find in the tree and climate environmental events. So things like precipitation, temperature, drought, and how they affect growth. Perhaps there's something that's impacted the tree that has caused it to reduce its growth for a period of time, as we see here. And maybe that's an insect. Insects can defoliate the tree, they can eat the phloem, the living tissue under the bark. It's going to cause a reduction in growth for a period of time. Or maybe it's some other injury that happened, or a fire that caused some damage to the tree, which caused it to reduce its growth. We look for that sort of sudden and severe reduction and then prolonged for that type of evidence of disturbance. And hopefully next week I'll talk about very specific disturbances, can dig into that in more detail. Sometimes there's just one event year that we're looking at. So one narrow year amongst, say, a period of relatively normal growth that could be indicative of extreme climate event like a drought year. Or we look for maybe more obvious evidence of trauma like scars. This is an example of a fire scar that I found in Montana at one of my study sites. I was actually there to study avalanches, which also can leave scars, but there were examples also that there was fire on the landscape. And we talked last week too about frost rings. Frost rings happen when you have extreme cold event during the growing season. So that's the important part. There are lots of questions last time. It's during the growing season, and it causes damage to the cells of the tree that leaves behind this sort of jagged, ragged-looking, almost scar-like damaged tissue that indicates there was an extreme cold event during the year. And it turns out that these, in my white bark pines, in my dissertation in the greater Yellowstone region, corresponded to volcanic eruptions that caused cooling events that affected the entire northern hemisphere. So I still think that was pretty cool that I found frost rings in Montana and Wyoming that were caused by volcanic cooling from a volcano in Peru and other sort of subtropical regions. So it goes to show also the spatial scale of the impact of these events. And then the other thing, and especially something I've been looking at a lot more lately in Kentucky, is using tree rings for evidence of land use change, of human impacts on the environment. In Kentucky, a lot of our old growth forests were cleared for agriculture, for timber, and they remain cleared now, in some cases, in places like the parklands of Floyd's Fork or in Jefferson Memorial Forest. Some of that has been allowed to return back or reforest over time. And when I went out, I didn't expect to find really old trees because everything had been cleared, but it turns out they're still around. Last time I talked about the tree in Cherokee, it's 400 years old. Trees in Iroquois are about the same age as well. Found some trees in Bernheim that were also that old. So they're still there. They're the survivors. They were there when it was old growth. They survived the clearing, and now they're there still as the forest closes back in around them. And hopefully in the next and future classes, I can talk about some of those stories that I've uncovered through tree ring records here in Kentucky. So today I wanted to talk about the tools of the trade. And to orient you before we go outside, there are 3 ways that I typically take samples from trees. The main way from living trees is the increment core. So we're going to get an opportunity to do this outside so you can see what that is like. Got a nice, sharp, clean increment bore, so it should be easier. But as you turn that one crank today, think about doing that for, say, 20 trees all by yourself or maybe with one teammate. That's what a field day is like. And actually, I've been out a lot in the parks around here, coring white oaks for an urban heat island related tree ring project here in the city. We mount them and stand them up, as I have examples of over here. The other way that we collect samples is with a drill and a different type of drill bit. So when we're working with archaeological timbers, it's drier, typically harder wood. It's been dead, for 100, 200 years. What we find when we try to take a sample with the increment borer is that the wood will tend to twist or break, or you're taking such a tiny core that you hit one insect hole. And if you've ever looked at a cabin or some old timbers in a building, there's lots of that. If you hit one insect hole, your core is broke. So we take bigger cores so we get more wood. It's more likely to stay intact. And we do it with a drill, so it's more likely to get into that hard, dry, seasoned wood. We won't be using this because this definitely takes a little bit more practice to use correctly, and it is more dangerous. The increment core we'll use today, not dangerous at all. This tool has the capability to break your wrist if you don't know what you're doing. So we use cordless power drills mainly because I go a lot of places where there is no power. So good batteries, lots of them. And this is specifically an archaeological drill bit. It's actually about 12 millimeters in diameter, so it's much bigger. It's about a ½ inch, or about as big as a thumb is the core you're taking out. And just like the increment borer, they work the same way. It actually drills out around the core and leaves the core intact, attached to either the living tree or the timber. You're just cutting out around it. Then you extract it after you're done. So this is kind of an aggressive tool, but it's designed that way for a reason. But because it has the teeth and things that it does, and you're using a power tool, it's a little bit more dangerous. I have a video to show you of what sort of the end result is of the archaeological, and I would like to talk more about archaeology in a future class. So here the cores are still actually inside the log. I've just cut out a hole around them. And then you extract them. This is from a structure in Ashland. And this is actually the ideal situation. They're all still in the log, and you just come through and pop them all out. Doesn't always happen that way. Sometimes they get broken up. More often than not, they get broken up. And you're doing a little bit more puzzle work. But this one, you could just stand in one place, and they were going so quickly, too. It was a really great sampling day. That's what they look like coming out. And again, I have a few examples of those for those interested at the end of class today. These chunkier cores that have come from historic buildings in Kentucky, if you're interested in taking a look at those. And then the last way we take samples is with a chainsaw. I did not bring a chainsaw today. Typically, this is for already dead and down stuff, or maybe a log from a log cabin that's already been removed from the building and we can have at it. We actually prefer these full cross sections because we get a ring all the way around the tree. Last week, I talked about how there can be locally absent rings that might pinch in and out or disappear on one side, and you can find them easier if you have the whole cross section. It's just easier to say, if you're like, is that a ring? Is that not a ring? If you have the cross section, you can sort of follow it all the way around until you're like, oh yes, it definitely is. If you had just taken a 4 millimeter core through there, that's all you got to look at. So cross sections are nice if you can get them, but most of the time we're working with cores. The end result being either these archaeological cores, a cross section, or the 4 or 5 millimeter ones we take with the increment borer. We sand these up to basically furniture grade polish, usually flattening them out with a high grit sandpaper and then going all the way up to any woodworkers in the room to like 400 on a belt sander or bench sander, and then hand polishing, sometimes up to 1200 or so. We want to be able to see the cellular structure of the rings under a scope. You want it to be polished well enough that you can do that, because it's so that you can get the highest precision measurement of the ring width that you can get. It's also so that those other things we look for, so we look for changes in growth, and it's, if you haven't even looked at these before, your eye can probably pick up on like slow, then fast, because there's these bigger, darker bands in this region on this oak. We have some American beech, poplar, and ash, all things I found in cabins here in Kentucky. So we look at those changes in growth, but we're also looking for evidence of trauma or damage. That can be evidence of disturbance. In the case right here, this is a zoomed in picture of mountain hemlock from Mount Rainier. Here in the later portion, and actually this is, see the cells? Can you all see them? That's how we want to sand it. We want to be able to see the cells. And you can actually see how the cell walls get thicker and thicker, and the luminary is sort of the cavity in the middle, gets smaller and smaller as you go throughout the year. You're going from the early wood to the late wood. And then here in the late wood, we have these traumatic resin ducts. So D-U-C-T, duct. So they're traumatic resin ducts, or TRDs for short. I often just start talking about TRDs and everyone's like, what? Slow down. TRDs, traumatic, so they indicate trauma. They're transporting resin to an injury in the tree. When you get them all lined up like this, that tells you that that tree is pumping to something. Now, it could be a scar. It could have lost a large portion of its canopy. Something happened to that tree. And we hypothesized that at Mount Rainier, this was snow or ice damage, something that happened during the winter time. We had a hard time getting them to line up. So we also want all the trees to indicate the same year. That supports that there was some kind of event in that year. But if every tree has a different year, you're like, okay, well, I don't know. Something affected each tree individually at some point, but no like widespread stand level, forest level event. We look for changes in growth like this here. This is 1950 with the 2 dots going to 1960. You see it's growing relatively quickly in 50, then 51, then 52. It's half or less than half of the previous year's growth. And then there's reduced growth for a period of time. It turns out, so this is actually a core from red spruce in Great Smoky Mountains National Park. For my master's thesis, I studied landslides in the Smokies. In 1951, in September, there was a cloudburst. Anyone know what a cloudburst is? Yeah, a lot of rain very suddenly, quickly. So it's like the cloud just burst and released all of its water all at once. So September 1951, in the Smokies, there was a cloudburst event. This is on Mount LeConte, if anyone's been there before. That triggered landslides. Now you might ask, well, if it's 51, why is the growth reduction in 52? It's because the event was in September 1951 at the end of the growing season. So you don't see the impact to growth until the next year. The picture at the top right is a fire scar in an Engelmann spruce from the Greater Yellowstone. There's a few things that are interesting. This tree was 100 years old. I don't have anything on there for scale. It was 100 years old when the fire went through. The fire maybe killed almost half of that tree, and it has grown back over top of that scar. Almost completely it's cut off, but you can see the scar in the lower part of the image. And the dots, so it maybe took it another 100 years to curl over to right here and seal up that wound. But we can follow that scar. If we follow it around to right here, we can actually see the year that that fire occurred. And whether it was a spring fire, a summer fire, or a late season fire. So So we can pinpoint it not only to the year, but to the time of year that the fire came through that system. And we could see if that fire affected a lot of trees to see the spatial extent of that fire. We can see how often fire occurs in that ecosystem and what drives it. And this is especially helpful, all of these things, for forest conservation and management. Say you're wanting to do prescribed burning and you're interested in how often fire came through that forest in the past. Tree rings could tell you that information. So this is the recap before we go outside. And it's sort of the preview as well for the things I intend to talk about for the next couple classes. So trees help us understand the past. We can look at how trees have responded to change through time, whether that's climate change, environmental change, human land use change. I mean, if you think about it, some trees just sit in one spot for hundreds to thousands of years. The oldest living creatures on our plants, they're trees, they're 7,000 plus years old, and they've just been in one spot for that long, recording everything that's happened around them. Understanding how this response to change varies by species, by environment, can help us inform the future. Which species are more drought tolerant than others? Which species are adapted to fire versus not? Which species persist and which do not, and why? So we can understand climate and environmental extremes. Understanding the past helps us put what's happening right now into historic and prehistoric context. Is what is happening now unprecedented in the history of humans? Is it unprecedented in the history of Earth? We use things like tree rings and other proxies that can take us back even further in time to help us understand that. Understanding how often environmental events occur. So how often have fires moved through? How often do landslides occur on this scar? How often have avalanches? How often do insects come back, and why do they come back, and what sorts of conditions might prompt a wider spread outbreak? And understanding, again, how current conditions compare to the past. So putting what's happening today into a longer-term context to help us better predict the future. So understanding how things have responded to change in the past can help us or inform how those things will respond to change into the future. So that's really the basics of tree rings. I wanted y'all to have that sort of grounding again before we go outside, because I want everyone, with this many people, it won't take too much. Not everyone has to if you don't want to take a turn, but everyone who wants to try it out can take a turn with the increment borer, and I'll demonstrate how we take a core outside.
Thank you very much. So here's how this is going to work. I think the easiest way to do this is either the elevators or the stairs. We're going to meet in the lobby directly in front of or near the elevators. Once we're all there, we'll just say raise your hand if you're here. Then we'll go out the front door, down the ramp, and around this way. The tree we're going for is on the 3rd Street side, and we'll congregate there. And then we'll do... This is so exciting. We'll do the tree coring. So I'll meet you guys up there. You can take the stairs or the elevator, and once we're all accounted for, by show of hands, we'll go. Yes? Depends on how much time we take up there. I would go ahead and leave your stuff here. I can lock the door so that it will all be safe, and then we can come back at the end.
That's it.